Good morning, or good afternoon, everyone. Welcome to X's booth on the Paris Motor Show 2016. Appreciate you joining us today. I'm going to do just a few minute introduction to the company so you understand what we do and our role in the automotive industry, the role we play in vehicle design, vehicle development. Most of the vehicles you see here at the show were developed in some way at some level with our products and technology used by the OEMs in the development of their vehicles. So we'll talk a little bit about what we do and how it has an impact on the industry, in particular around the field of fuel economy, CO2 emissions, a major challenge for this industry. The technology that we're going to show, the platform that we give our customers, enables them to better design their products in a more efficient way and bring better products to market more effectively. So what you see here on the screen is a little bit of what we do. My name, by the way, my name is Steve Raimondi. I'm CEO, President and CEO of the company, one of its founders. And we are based in just outside of Boston in the US and have a global customer base and a global presence here in Paris and all over the world to be near our customers. What you see on the screen here is a release last year by Jaguar with the F-Pace, and you can see here a bit of the aerodynamics. One of our things our products do and help our customers do is to simulate and understand a complete virtual engineering environment to understand the aerodynamics, the thermal management, the wind noise, the comfort, and the capabilities around these systems, in and around these vehicle systems, so they can better design those capabilities. So here you see just a little bit of this car. This is the simulation model. All of this is created digitally. This is the digital model within our simulation platform, showing you just a bit of the aerodynamics of this vehicle as the air comes into the front bumper and how the customer is working that design to efficiently move that air around the vehicle, around the front bumper and under the tires to produce better efficiency, lower drag, better fuel economy, lower CO2 emissions. So if I start, so our mission here is, again, another vehicle shown. You can see the aerodynamics and the complexity of the aerodynamics around these vehicles. What we do is we help our customers work in the studio from day one as the vehicle is conceived and as customers are conceiving and designing these systems. We want to be able to provide them feedback and a platform that allows them to understand, if I make these changes or if I design the vehicle in this way, how does it perform? What's the noise? What's the temperatures? What is the aerodynamics? What are the emissions of this vehicle under this design constraint? So all of that has to happen. We have to deliver very complex physics modeling to enable them to do that. And you can see very complex physics going on around this car, very turbulent flows. How to manage this is very sophisticated to predict. We use very complex computer algorithms to actually help them do this at a computer and give them that complete digital environment to do that. So our products, our mission really is to help our customers develop better products through the use of simulation, right? How does my product perform? How is it going to behave? How do I work with the studio to create both an aesthetic, a beautiful product that has the passion and the market presence that we want, but yet has the technical performance that we need? Another picture here, again, of that F-Pace, but now looking at the aerodynamics. One of the things that Jaguar mentioned about their F-Pace is proper lift balance, equal lift balance between the front and the rear wheels, a better driving experience for the customer. So not only fuel economy, but handling. And you can see here just, again, another animation of just the basic aerodynamics around the envelope around this vehicle. Right? And many of these surfaces, hundreds, or in this case, thousands of simulations are being done to test lots of what-if concepts as the vehicle is coming together and designed. Again, the perspective from the back. A little music for our... And you can look from the back as well, the rear spoiler, the underbody, all of these components come together to produce the aerodynamics of this vehicle and how it has its impact on fuel economy. So if we just talk just a little bit about the economics at play here, certainly as a vehicle design progresses from the early days of the concept, the first concept in the studio, maybe an advanced design or a concept vehicle that's being produced, as that vehicle matures and develops, in the first few months, that design solidifies. Okay, so the upper surfaces, the metal, the sheet metal components of this surface get solidified as it comes out of the design studio and moves into engineering. So the goal is, if engineering is going to have an influence on that vehicle, we've got to be able to work and enable our customers to work in the studio with the designers as part of the creative process. That's why everything you see that we do is rendered photorealistically. Even though it's a computer model, we've got to put it in realistic environments We got to give that designer that aesthetic view of what the design looks like as we're looking at thousands of different combinations or design parameters that we want to improve. So as the design progresses, it solidifies, so we have less and less opportunity. So if I rely on physical testing for me to get my information about how the car performs, it's very late and oftentimes too late to fix the problems, right? And so you're making poor compromises late in the process. So we can help reduce engineering costs by taking prototypes out of the process, but most importantly for this customer base, we can help them avoid late stage problems. These are the problems they find as they drive their vehicles, drive prototype vehicles, on their proving grounds, out in the world, and they find problems late stage. Oftentimes these are thermal, noise-related issues, how to find these issues, how to discover what to do about it, and then the fact that you're very limited in time or ability to actually retool or redesign the car to fix them, right? So poor compromises get made when you find these problems late. So bringing that simulation up early stage enables customers to do this right up front. So when you build the first prototype coming off the factory, it behaves as you expect, and that's possible, right? And that's really what we're bringing to light. We have customers like JLR who have mentioned publicly that they have a vision for 2020, the year 2020. They want to be developing the vehicles without prototypes. Right? And so we are working collaboratively together and strategically to actually build a capability for every single one of their tests to be able to do that in computer modeling or virtual engineering instead. Okay, and then lastly, you have all the post-launch economics. If you have thermal issues in a vehicle and parts are overheated and experience over-temperature components, that'll result in higher warranty costs, higher failure rates in the field. Okay? And so that is a big economics at stake of getting this right, especially with regards to thermal. Okay, so then we look at the dynamics of the industry. We talk about the engineering companies and customers that we support. And in this case, there's a lot of forces in play on the engineering companies and the engineering customers. One, regulations are continuing to change. The emission standards, the CO2 targets are dramatically being forced to improve. They have tremendous efforts to improve and design more efficient vehicles going forward. So the emissions piece, both CO2, NOx, and noise, along with safety and rules. If you're racing, you also have to deal with regulations, but in a different way. But the regulatory bodies determine what kind of parameters you can play with on the vehicles. In addition, the industry, as you see here today, continues to expand the proliferation of models. They continue to develop more models on common platforms. That's differentiating the products for the customer base, which the consumer really prefers, and allows the OEMs to actually not have to move or discount or use incentives to move higher volume, right? They can do that with fragmentation. But they need a more efficient engineering process to do that. So the engineers are getting more models to do. They've got harder goals to reach, which means they have to work harder per model to get to those targets. So all of this is putting tremendous pressure on the engineering, and at the same time, they got to do this and still make a beautiful product, right? That's aesthetically pleasing, because that's really the dominant factor in this industry, still continues to be. So we always talk about, as engineers, it's quite fun because it's a fashion industry with enormous technical engineering performance requirements that have to be also achieved simultaneously. And the fun part about it is what worked before in the previous generation of vehicle is often not what you want to do in the next. So you have to throw away what you've learned and what you've done, and you have to find new solutions and new approaches. And you constantly see that here in this industry. So lastly, maybe we could say just a couple words about the Land Rover Discovery that was just launched. In particular, Jaguar Land Rover mentioned they did over 1,000 simulations on this vehicle as part of the design process. You see things like the air curtain in front was an opening to help manage the flow around the tires, and again, to improve fuel economy. How do you improve fuel economy of a 7-passenger, rugged, outdoor, off-road capable vehicle, at the same time make it efficient? Right? These are not easy engineering challenges. Another key component, the rear spoiler, you'll see just one thing you can see. These are the obvious things you can see outside the car. You'll see the slotted rear spoiler, and that slotted there is based on a new capability from us that allows our customers to test the impact of soiling and dirt management along with the aerodynamics. So how do I make an aerodynamically efficient spoiler, critical for fuel economy, and those slots are opened up to actually provide some air down the backlight so that they reduce the amount of soiling for consumers. So with that, I'm going to talk about just one of our partners here, Denso. Our partner is here. We've just released and announced a partnership in July with one of the top suppliers in the world, and we are partnered together on their thermal management products. This is for both engine cooling and passenger comfort, where part of the challenges we have is our customer base needs the capabilities of geometry and details of Denso's products early. If we're going to do this early, they're missing design components. How do we help them do that? So maybe with that, maybe I'll introduce Yasuda-san, who maybe will say a few words about what we do together.
Thank you. Yeah. My name is Yasuda, head of the powertrain cooling of Denso. And we have worked together almost 10 or 15 years as a customer and the suppliers. But now we are convinced to work together as a partners to give the engineering benefit to our main customer with the vehicles. And through this strategic partnerships, we believe to give the development accuracy and efficiency and inspiring. And probably in a couple of years ago, Denso can give the quite impressive concept through these collaborations. Thank you.
So the critical piece here is, again, that platform to enable our customers to do this engineering work up front, they need the details, right? The details of a cooling module system, how you duct it, how you install it, 2mm gaps on a 1 meter size vehicle makes a big difference, right? To the aerodynamics, to the cooling efficiency, to how the flow is managed under hood. And so it's critical that our customers have that geometric detail from the supply chain so they can do this work early. Right? And that's been missing. And so to a large degree, oftentimes, the customer, the OEMs, are not really experiencing these systems until the very end of the design when they install Denso's components into a physical prototype and then start to discover how it performs and maybe the things that they've done that don't allow that to work properly. And lastly, I'd like to introduce Jacques Nicolet, CEO of Onrock Automotive. His car is sitting here, and a picture of the work we've done in simulation. Together as well on motorsports activities.
I will try to be as fast as Steve with my English, but it will be very difficult for me. We worked with EXA since we decided to start this project, our new LMP3, which is a sport prototype with a complete new regulation in endurance. And for us, the work we made with EXA was very important to achieve the goal we have in this new category. The one very important was we have a cost cap, very difficult to achieve for us. And so we transfer with EXA all what we knew on our sport prototype LMP2 on the LMP3, and with also we adapt the difference in the regulation between the LMP2 and the LMP3. And clearly, it was for us a big success, because we thought at the beginning that we sell on the 4 years period of homologation of the car. We thought selling 20 cars, and 1 year after the presentation in the 24 hours of Le Mans, we delivered the 50th in China this week. So it's a real success, and to go on our collaboration, we have presented last weekend in Spa our new LMP2, the GSP 217, and we do it with EXA for sure, and we have now the same problem to adapt this new LMP2 to the new category in the States, the Daytona Prototype International, which is made on the same base of the LMP2, but with a lot of difference in aerodynamic and also with a new engine, so new difficulties for the cooling and so on. And we have to deliver this car in 2 months in the States. We signed one agreement 10 days before with Nissan Nismo. And so we can do it only because we have all the tools we can have with EXA.
Thank you. One of the key designs here in this vehicle was how to keep the driver, how to cool enough,
yes,
got enough air into the
sure.
driver capabilities. So you, I don't know if you want to comment.
We made with EXA and the Stand 21 a big job for the cooling of the driver in the car, and because for this category we have a lot of gentleman driver, and they need more fresh air than a young professional driver.
And so getting that air in, you can see the air intake, and then managing that air efficiently out. You see the exits, this is all the air going into the cabin. You see the streams now of air coming back out of the cabin, and how they interact with the rear wing and downforce, all interacts. So you can even think around, you just want to cool the driver a bit, and you're changing the aerodynamics of the car. And all of that needs to be understood, right? And better to do it digitally than on the track.
Thank you for your help, Steve.
Very good. So with that, I'm going to turn, we can conduct a demo here of, we'll do the Honda R-Sport, if you like, with Paul Stewart.
John, should we do the app pace?
Can we do the glasses? Yep. Great, thank you.
Are we doing 3D or
Yeah, we can do 3D. And hi, I'm Paul Stewart, Senior Director of Design and Visualization at EXA. Let me invite the journalists up. What we're going to do now is see this in 3D.
Mike?
So please grab some glasses. I've turned them on, we should be set.
Ian?
So step right up, grab some glasses. So one of the, as Steve said, it's very, very important to understand the performance of the vehicle very early in the process. But to really do something about it, to really change the design, the key is to not just to understand how it's performing, but to understand why it's performing. So what we're looking at here is a fairly common device on most cars. It's called a splitter on the front end. And what you're looking at is airflow coming in from the right. And when the airflow hits the car, you see that bright red. That represents pressure or downforce. So what you're trying to do with this device is generate a lot of downforce to give stability when the car is moving at high speed. Now, if I look underneath though, you watch the airflow come in, and it goes underneath, but it actually separates. It leaves the surface of the car, and when it does that, you end up losing some of the downforce that you could have generated. Now, the reason I'm showing you this is one thing to go in and say, gee, you need to change the shape of your splitter to the designer. But you can't go in and just dictate how the car's going to look. If you can explain why the car, why their geometry is deriving these performance values, then it's much easier to have that design conversation. So let's have a look on the outside here. For this particular image here, you see the splitter in the middle is bright red, a lot of downforce. But as the flow goes around the outside corner of the car, it accelerates. You see the flow beads turning red. They're going very, very fast. When flow goes fast, the pressure drops, and the tip of the splitter is actually not giving downforce. It's actually providing lift. So again, you can't really just tell people how to change the shape of the car, but if you can help them understand the results, help them understand how the flow interacts with their geometry, and how that geometry can be changed to improve the performance, then it becomes a very easy engineering discussion. We have a look on the side here. And again, you get that full picture of that flow coming into the vehicle, stagnating on the front, zipping around the side. And this is how a splitter works. Now, if I were to try and do this in 2 dimensions and wave my hands for 10 minutes, maybe you understand what I'm trying to explain, maybe we don't. But I think you can see with a technique like this, the ability to take our results and communicate them. To first figure out why the car is doing what it's doing, but then to communicate it to others so that you don't need to understand the physics, the complex equations. You just need to understand the motion and the time and the geometry of the particular design issue, and suddenly then our focus is on how do we improve the vehicle. Steve, did you want to, should we quit with that or should I go through the break?
Just do the break for a second.
Okay. Yeah. So let me show you another example here on this particular vehicle. Just particularly interesting if we switch sides. So this particular vehicle has an active brake duct. So it ingests air and it's going to, we'll track down and we'll see this in a moment. It takes this air through the duct and it blows it onto the brake disc. So after heavy braking, the disc itself becomes very hot. If you let it continue to stay hot, the brakes don't function very well. So you have to cool them off, and this is a popular technique. 20 years ago, these were decorative on cars, but most cars these days are starting to get these active ducts. Now by active, if I close the duct, you can see the flow just travels around the outside of the vehicle. And if I open the duct, it travels down inside, which is where we're going to go here. So here we're right up to the edge of the duct. And let me take you down into the duct. Again, where the flow is red, it's moving very quickly. And the design issue here is this piece, this tan-shaped piece. Its role, or its task, is to take that flow and deflect it as it comes in. And you see in the back, if I take away the tire and the brake caliper, you see the brake disc itself, where it's bright red, it's giving off a lot of heat. So the objective of this particular feature, this brake duct, is to blow air on there and allow it to cool down quicker. But really, to do that, let me change views a little bit here. What you have to understand is how that flow comes in. It's a bit of a billiard shot. It has to hit that deflector, snake around inside the tire, and get up to hit a relatively small target in order to provide better cooling. And this one more so than any of the others. So now you get an appreciation of how this particular part functions. Here we get a chance to see how the flow is moving in, hitting that particular deflector and coming inside the tire. Now for this earlier design, it's an older design, you can see actually with the transient, the very detailed solution that we have, you can see some of the flow hitting that deflector and not actually making it into the brake duct. So here you're looking at a problem that involves thermodynamics, aerodynamics, geometry, design, very, very complicated. But the point is, in an environment like this, we can look at this very quickly and start to reason out how we would make some modifications to this design to improve the performance. We can see the relationship between results and design, and from there we go forward.
Great. All right. Thank you, Paul. And I think maybe you can see a couple of practical examples of how the technology is used here in the product, and I'd be happy to answer a Q&A here after the session ends. If any of the journalists, members of the press have any further questions or discussions. Great, thank you all.
Okay.